So now we're going to look into actually working with numbers directly in Python. And numbers are one of the built-in standard types of Python, of which there's numerics, sequences, mappings, classes, instances, and exceptions, most of which we'll eventually cover in this course. So Python has three basic types of numbers. Well, I consider basic integers, like we talked about in the last notebook, reals, and complexes. Reals and integers are worked with directly. Complex numbers, you actually import a library, so it's maybe kind of unfair of me to say that it's one of the three basic types. But Python also has additional functionality for dealing with specialized applications, and this includes the decimal module from the standard library and fraction. And decimals for working with fixed precision floating point numbers. So, like I mentioned, currency, and fraction is exact representation of rational numbers. These are fairly specialized. Complex numbers are general, but kind of limited in the kind of scope you'd likely run across in biomedicine. Integers and floats are really the pieces that we're going to be working with the most often. So let's talk about how Python, or computer programming language in general, encodes integers. So integers can be encoded in the following ways. Decimal notation, base 10, which is what we're most commonly use. Hexadecimal, which is at base 16. Octal, which is base 8. And binary, which is base 2. And base 10 is the default. Why the choice of these? Well, it's kind of rooted in the architecture, which are transistors, where I have a concept of an on-off or a 0-1. That's where our base 2 comes from. The importance of octal base numbers in computer programming is that a byte is 8 bits, and hexadecimal is 2 bytes, and that's kind of more archaic relationships, but while for the most part in Python these details will be hidden from us, occasionally you will run across the need to be able to work with hexadecimal, octal, or binary numbers, and so it's valuable to be familiar with them. So hexadecimal numbers use a base 16. So we need 16 characters to represent numbers in hexadecimal. So if we think about base 10, we have the 10 digits 0 through 9, and so we need to add 6 additional characters, and we just use the first letters of the alphabet, so A, B, C, D, and F. We declare that this number is a hexadecimal number by preceding the number with 0x. So here I'm typing 0x543EF, and then if I print that, Python is automatically converting that to a decimal notation. So this is in hexadecimal. This is the number 345,071 in decimal. Octal numbers are similar. We proceed encoding a integer as an octal number with 0, here we only have 8 digits, so we limit our numbers to 0 through 7. So here I'm taking the octal number 547, and that corresponds to the decimal number 359. Okay, here if I do 578, I'm getting an error, and this is saying a syntax error, invalid syntax, and what's happening is I only have 8 digits to represent 0 through 7, and so 8 is not a valid digit to be using in encoding a octal number. Okay, binary numbers. Base 2 is coded by preceding the number by a 0b. We only need 2 digits, so our digit characters are limited to 0 and 1. So here I'm declaring 2 numbers. This is the number 2. And then this would be the number 5. So when I add them together, I get the number 7. Okay, Python provides functions for converting between integer codings. So bin is a function that will convert something to a binary encoding. Oct, similar for octal encoding, and hex for hex encoding. So if I take my number, which up here was the number 2, and I print that in binary or octal, just do that. I'm going to split the cell. So it's taking the number 2 in binary and the number 2 in octal. Here I'm taking the number 2016 and representing it in hexadecimal. So that's the hexadecimal representation of 2016. Python provides the function int for converting numbers or strings to integers, and by default it will convert it to a decimal number, but it takes an optional keyword argument that I can tell it, no, this should be a base 16 or a base 2. So here I'm going to try to take the number 4.8 and convert it to an integer. And here I'm taking the string 67 and converting it to an integer. So let's see what happens. Well, here we get the number 4. So 4.8 is a real number. It has a decimal portion. So what Python is doing is it's just truncating it. And so I lose the decimal portion, the 0.8, and it returns me the number 4. And here it took the string 67 and was able to convert it to the integer 67. Well, if I take something like the string hello and try to convert it to an integer, I get an error message that hello doesn't represent any valid base 10 number. Here I have a string, and I'm going to tell it, oh, this is a base 16 number. And so then, yes, it does the conversion for me. And similarly, I can tell the numbers these other formats. So you see D is one of our extra digits for representing base 16, so this is a valid hexadecimal number. So that's kind of working with converting different base representations of integers. And in class we'll explore this more of what this positional base representation means as part of our in-class exercises. Here we can look at the different ways that Python encodes floating point numbers. And one of the easiest way to make a number a floating point number is just how we type it. So if I just type a 4, Python's going to look at what's the minimal representation I need to represent what you just typed. And the simplest representation of 4 is treating 4 as an integer. If I type a dot, a period, or a period in some number, then it's going to force this to be represented as a string, as a float. And so what we'll see here is we'll have a type of an integer, and then we'll have two types of float. And I can encode floats in different ways. For instance, I can do an exponential form. So this would be 4 times 10 to the 1 in either case, so those both should be 40, interpreted as floating point numbers. And similar to the int function, Python provides a float function. And another thing that Python will do is if I divide two integers, it will automatically give me a floating point number. And this is different than if you're working with Python 2 version like Python 2.7 versus the Python 3 that we're working with. In Python 2.7, it would return a truncated integer instead of a float. So here are some, just generating some floats. But it didn't know how to take my hexadecimal string and convert that into a float. So one thing I could do is I could convert this to an integer first, saying this is base 16. And then, what did I do wrong? Missing a parenthesis. Then, given that I convert it to an integer, then I can convert it to a float, which is the same thing I did down there. Didn't read ahead on my notebook. We can construct complex numbers by the notation of either taking a number and tagging on a j, which is the symbol in Python for the imaginary component of a number, or just like there's an int and a float, there's a complex function that allows me to provide the real and imaginary part of the number, and it will construct it for me. Given that I have a complex number, I can pull out the parts of it, the real and imaginary parts. And with all these numbers, we can do all the standard arithmetic things that we're used to doing with numbers. So we can do addition, subtraction, multiplication is the asterisk symbol. We can do division. Something that you're not maybe as familiar with that will actually make use of a fair amount is the modulus operator, and that's the percent symbol. And that will return the remainder that results from a division, and exponentiation, where we have two asterisk symbols. So that would be a number a raised to the power b. So here I'm just going to go through, I'm just doing these basic operations, and I'm going to say what is the resulting type that results from this. So I have 5 plus 3, that's a type of an integer. 5 minus 3 gives me an integer. 5 times 3 gives me an integer. 5 divided by 3 returns a floating point number. 5 modulus 3 gives me 2, an integer, and that's the remainder. So 3 goes into 5 once with a remainder of 2. And then 5 raised to the power 30 is an integer. And 4.3 modulus 2 gives me a float. So when we're working with the numbers, there's an order of precedence. Multiplication and addition, so multiplication is done before the subtraction. So in this expression, 5 times 4 minus 3, this would be, we'd first do the multiplication. 5 times 4 gives us 20, and then we'd subtract 3, which is quite a different answer than if we did the subtraction first, which would be 4 minus 3, which would give us 1, times 5 would give us 5. And here's a link to the how Python evaluates order of precedence that you can read through. And if like addition and it's multiplication and division have equal precedence, and so then it's done from left to right. Okay, if I mix types, Python's going to pick an expression that kind of takes what's the most data needed to represent the result. So if I take a float and I add it to an integer, my result will be a float, not an integer. And mostly, kind of the way I think of it is which number requires the most bytes to represent it, and that's what the resulting type will be, whichever one requires the most. So it's not, by default, Python will try not to throw data away. Python provides a round function for floats. So if I take 5.7, that will round to 6, but the type is still a, so if I print the type of round 5.7, it does return an integer, not a float. We can make comparisons with numbers. So if I want to say if two numbers are equal, I do a double equal sign. This is important because there'll be a frequent mistake of using a single equal sign, and a single equal sign isn't asking the question, are these two numbers equal? It's an assignment operator where it tries to assign the value on the right to the value on the left. So two equal signs is how we ask whether two numbers are equal. Not equal to is an explanation equal, less than equal to, and so on. So here, this will give me a Python error. I'm not asking is 5 equal to 4. I'm trying to assign the literal value 4 to the literal value 5. That is invalid. But I can ask whether 5 is equal to 4, and it is not. So some of the important numeric libraries that we'll be working with in Python include the math library. So this will be where Python provides function definitions for like square roots and cosines and sines. There's an analogous library, CMath, for working with complex numbers. We'll use this random module a lot, and this provides functions for generating pseudo-random numbers. We'll use this when we're doing simulations, for example. So for any one of these modules that are part of the Python standard library, I can learn what's in it with the dir function. So if I import math, this is telling me everything that's defined in that module. We'll talk about what these are later in the course, but we have an arc cosine, a hyperbolic arc cosine, so on. So a lot of detailed mathematical functions in there. Similarly, for the random function, we can do the help on random, and this will tell us if the developer's done a good job of providing help strings, of what are the functions that are defined in this module and how to use them. So let me scroll through that, and here, there's a uniform, so this will randomly select a number uniformly between 5 and 10. You can look at the documentation for what's the difference between uniform and random range. A Gaussian is a kind of a normal distribution where I provide what the mean value is and what the standard deviation is. And here's just kind of some explorations of the different functionalities that are in there, and demonstrating how we can use the fraction function to give it we give it a decimal number, and it's going to tell us what the ratio of the two, what the rational number is, if in fact it is a rational number.